welcome back to our discussion on multiple comparisons. In the last video, we looked at doing multiple comparisons using Fisher's least significant difference value, and we found how to calculate confidence intervals for the differences in our treatments. Now, Fisher's least significant difference is a liberal type multiple comparison test. However, a more conservative type multiple comparison test we can use is Tukey's honestly significant difference. Tukey's honestly significant difference is a very similar procedure to Fisher's least significant difference. However, our honestly significant difference value is going to be defined to be our studentized range value times the square root of the mean square error over n sub I. With Tukey's, n sub I must be the same for all groups, meaning each group must have the same number of replications. Now, we can use the computer for this. This function is in R. However, we're going to look at how we could calculate this both using Tukey function and in calculating this by hand. Now, this studentized range value, Q, is looking at the number of groups being compared. That's K. Alpha is the experiment-wise error rate for Tukey, and n dot minus k is the error degrees of freedom. So, how would we do this using R? Well, again, recall we're dealing with our crop data. Now, our Tukey's honestly significant difference value, that is our Q with the number of groups being compared, our error rate for our Tukey, and our degrees of freedom, times the square root of the mean square error over the replication size. So, again, K the number of means, alpha the experiment-wise error rate for Tukey, and n minus k its degrees of freedom for error. Now let's suppose K is 4. So we have 4 groups we're going to compare. We want to set alpha to be 0.10 and our degrees of freedom error 12. Well, in order to determine what our Tukey value is, we're going to use the Q Tukey function. Now, notice, we want P equal to 0.90. And this is because we're looking for the upper tail, 0.10. Our number of means is 4. Our degrees of freedom for error is degrees of freedom. And so what we get when we run this is a Tukey value of 3.620708. And so we'll set our honestly significant difference value for an alpha of 0.10 equal to our Tukey value times the square root of the mean square error over 4. And we get an honestly significant difference value of 3.162176. Now, much like we did with Fisher's least significant difference, we're going to compare our ordered means to our honestly significant difference and determine if we have difference. So, again, D was the lowest, then A was second, then C was third, and finally B was the largest. So if we look at the absolute value of D minus A, we see we get 0.6875. This is less than our honestly significant difference value, so these are similar. Now, if we compare D and C, we see we get a value of 1.18, again, less than our honestly significant difference value, and so these are similar. Now, when we compare D and B, we see we get a value of 3.7. This is greater than our honestly significant difference value, and so we can see that these differences in means are different. Comparing A and C, we can see that we've got a value of 0.4925, less than our honestly significant difference value. Likewise, A and B, less than our honestly significant difference value. And finally, comparing C and B, we see that this is less than our honestly significant difference value. And so what this is saying is that only D and B are different. Everything else is similar. Now, much like we did when we did our Fisher's least significant difference, we have arranged our means from least to greatest, and any underlying means are similar. So D, A, and C were similar. D and A, D and C, these are similar. Now, we look at A and C and A and B. We can see A and C and A and B are similar. However, D and B, these were different, and so they're not underlined. Suppose we wish to find a confidence interval for Tukey's honestly significant difference. Well, this is simply y bar I minus y bar j plus or minus the honestly significant difference value, but very similar to how we did our Fisher's least significant difference intervals, except we're replacing our least significant difference here with our honestly significant difference value. And when we run these, we see that the confidence interval for D minus A is negative 3.84 to 2.47. Zeros in the interval, these are similar. And when we compare D and C, negative 4.34 to 1.98, these are similar. When we compare D and B, negative 6.86 to negative 0.53, we can see that these are different. Zero is not in the interval. When we compare A and C, negative 3.65 to 2.66, zeros in the interval, these are similar. A and B, negative 6.17 to 0.1496. So we can see that A and B are similar. And finally, when we look at C and B, negative 5.68 to 0.64. These are similar. Suppose instead we would rather use an alpha of 0.05 in our interval. Well, now, again, we need p equals 0.95 in our Tukey quantile so that we can find the value that gives us an upper tail of 0.05. We still have 4 means. We still have n minus k equal to 12. And now how does our Tukey value change? Well, now we get a Tukey value of 4.19866. And so multiplying this by the square root of our mean square error over 4, we can see that our honestly significant difference value, 3.5989. And so, again, finding our confidence intervals, but now with a Tukey probability of 0.05, we can see that, well, D and A still have 0 in the interval. They're similar. D and C still have 0 in the interval. They're similar. D and B, however, still do not have 0 in the interval. A and C have 0 in the interval, so there should be no difference. A and B have 0 in the interval, so there should be no differences. And then C and B have 0 in the interval, so there should be no differences. Now, if we go back and compare, again, our Tukey value for this is 3.598941. So D and A are similar. D and C are similar. D and B now are different. A and C are similar. A and B are similar. And C and B are similar. So, even with a smaller error rate, we see that D and B are the only differences. Okay, we've created our confidence intervals at alpha is 0.10 and then alpha of 0.05. We can actually use the Tukey HSD function in R to do this same thing. Notice there's a linear model function nested inside an AOV function, nested inside the Tukey HSD function. I've specified order equals true. I've also specified that my confidence level is 0.90. So if I run this, notice here are my comparisons. A minus D, C minus D, B minus D, C minus A, B minus A, and B minus C. Now, this is slightly different from how we looked at this by hand. We looked at D minus A and D minus C and D minus B, and A minus C and A minus B and C minus B. However, if you look at your differences, you can see that, well, we only have one difference that's greater than the Tukey value. We have our lower and upper confidence interval values, and we have our adjusted p-values. And paying close attention, we can see that the only significant difference lies at B minus D with alpha of 0.10. We can then plot these in a Tukey plot. And notice A minus D, C minus D, C minus A, B minus A, and B minus C all contain 0 in their interval. However, B minus D does not contain 0, suggesting this is different. Now, what would it look like if we were to do this at 95%? Well, now we just change our confidence level to 95.95. And notice, we still have our differences, same differences. Our intervals have changed slightly. We'll just look at B minus C, negative 0.642 to 5.68. Notice it's changed a little bit. We still have our adjusted p-values. And notice the only significant difference lies at B minus D, even at 0.05. So what would this look like if we plotted it? Well, now, notice A minus D, C minus D, C minus A, B minus A, and B minus C all contain 0. However, notice now that our B minus D comparison, our interval almost gets to 0. However, 0 is still not in the interval. Therefore, these are different. Okay, that's it for our discussion of Tukey. In our next video, we will look at Bonferroni and how we can control experiment-wise error rate. See you then.